Thank you. Okay, so my name is Or, and I work in theoretical computer science, mostly complexity theory. And what we are trying to do in complexity theory is to understand which tasks are hard for computers to solve. It is what things are hard to compute. And to be more concrete, let's take a Boolean function, f, which will be from 0, 1 to the end to 0, 1. And we want to prove statements such as it's not possible to compute f efficiently. That is, no efficient algorithm can compute f. The way I put it, it sounds very informal, but we actually have very formal models of computation, and we can say formally statements like those models of computation cannot compute the function f. Unfortunately, since those models are pretty general, since they capture every possible efficient computation, and as we know, computers can do a lot, it's very hard to prove things like it's not possible to compute f efficiently. So what we do in my field instead is we settle with much more restricted and weaker models of computation, and we try to prove that they cannot compute the function f, and hopefully they will serve as a good milestone. Once we solve this conjecture, we might be able to prove it for stronger computational models. So one such weak model of computation is formula complexity. So we look at Boolean formulas, the one you know, that use Boolean variables and use operations like Boolean AND or Boolean or say negation. And we ask how efficiently can such formulas compute f. For example, what is the smallest Boolean formula that computes the function f, that represents the function f? And say we measure the size of a formula using the number of Boolean operations. And in this case, the state of the art is a result by Hastad that shows that gives some explicit example of a function f for which you have to use formulas of size omega of n to the third to compute. Say just n to the third. So we have an example of a function that can be computed by formulas of size n to the third, but cannot be computed by smaller formulas. And improving on this state of the art, and say finding an explicit function that cannot be computed by formulas, say, of size n to the 10, or ideally cannot be computed by any formulas whose size is a polynomial, is kind of a holy grail of complexity theory. And we would very much like to solve it. And the question is, how do we even analyze such questions? How do we solve such questions? So there are a few techniques. I would like to describe one such technique. And the technique is called the Karchmer-Wigderson games, where Wigderson is Avi, who sits here. Avi and Karchmer discovered in the 90s that for every such function f, there exists an equivalent or an analogous communication problem, such that solving the communication problem is as hard as, say, call this communication problem PF. Solving PF is exactly as hard as computing f by a Boolean formula. So what do I mean by a communication problem? It's sort of similar to the kind of communication problems that Gilad talked about in her talk. So again, we have two parties, Alice and Bob. And the communication problem of PF will be defined as follows. Alice gets string f such that that is a, sorry, it's a 0 of the function f. And Bob will get a 1 of the function f. And obviously, x and y must be two different strings. And Alice and Bob would like to find some coordinate j such that x and y disagree or differ on the coordinate j. And Alice and Bob would like to find j by communicating as few bits as possible. And now the equivalence between those two problems can be stated roughly as saying that Alice and Bob can do it by communicating c bits if and only if f can be computed by formulas of size two to the c. This is not completely correct, but it is roughly correct. Okay, so and now during the last year, and this is also my goal for the few more next months, we are trying to prove formula lower bounds using this general idea of equivalence between formula complexity and communication problems. Hopefully, communication problems is something that we have more intuition because it deals with information rather than computation. So in the time that's, okay, do it here. In the time that is left, I'd like to give one example of how can we prove, a second, of how can we prove lower bounds using this technique. So let's assume that f is the parity function. That is f of x equals 1 if and only if x has odd number of ones. In this case, we can actually show that the formula complexity of f of the parity function is n squared. That is, you need the formulas of size n squared to compute parity. And the proof is very easy, and I'll try to give it now. So again, we have Alice and Bob. And Alice gets a string x that has an even number of bits. So let's say even x. And Bob gets a string y that has an odd number of bits. Oh, sorry, odd number of ones, sorry, right? And they want to find j such that xj is different than yj. And the basic idea of the proof, I won't do it formally, but I'll give the idea, is that first of all, we can restrict to the case in which x and y differ on exactly one coordinate. This is in general possible because, well, for every even string x, if we flip one coordinate, we get an odd string. So in this case, the index j that they wish to find is determined uniquely. There is only one such j. And now the point is that let's look how the communication looks from the side of Alice. So Alice sees this, has her string x, and by looking at the string x, she really cannot tell anything about j. She doesn't know anything about j. Because for every coordinate of x, if we flip it, we get an odd string that could be given to Bob. So Alice really has no information about j whatsoever. But we know that by the end of the protocol, Alice must actually know j. So this means that she must have learned log n bits of information from the protocol, from the communication, because one needs log n bits of information to represent j. But if Alice learned log n bits of information, it means that Bob sent log n bits. On the other hand, the same argument applies to Bob. Bob also doesn't know anything about j, and he also has to learn log n bits of information on j by the end of the communication. So it means that Alice must also have sent log n bits. All in all, they both sent 2 log n bits. And by this connection, we get that in order to compute parity, you need formulas of size n squared. I gave a very intuitive sketch, but actually this can be translated quite easily to a formal argument. So this is one example. And we are now trying to see whether those kinds of arguments can be improved to give even stronger formal lower bounds. Thank you very much.